So, and let me share the screen. All right. So we have started recording now. Can everybody see the screen?
Yes, sir.
Okay, thanks. So let me erase this stuff here. It's not really necessary. Okay, so I just want to start by stating the fundamental theorem of linear programming that I mentioned yesterday as well. So I think from now on, I intended to do this earlier as well, but anyways, I did not because I was using terms different from the text sometimes. So from now on, I will try to give a number to the theorems and main results. And in particular, I will specify which book I'm following. It's mostly for me to keep things a bit organized. And in case you need to refer to some theorem in your assignments or something, then you can use this numbering scheme, right? So if I write GKT, I'm referring to the first text, Ginin, Kahneman, and Tunchel, who are the authors, right? But as I said, you don't need to have the text for this course. I'm expecting the course to be complete and self-contained with respect to the lectures and the assignments, okay? So the fundamental theorem of linear programming, which we discussed yesterday, is that if you are given any linear program, let's say LP star is any linear program, right? We know what a linear program is. You're maximizing or minimizing an affine function with respect to linear constraints that are less than equal to, greater than equal to, or equalities. Right? Then exactly one of the following holds. The first possibility is that the linear program is infeasible, or it is feasible, and in which case we have two other possibilities. Either it is unbounded, which means that for a maximization problem, you can find feasible solutions with arbitrarily large values, right? For any constant k, you can find a feasible solution whose value is strictly greater than k. And for minimization, it would be strictly lesser than, right? And the last possibility is that the linear program has an optimal solution, right? Sometimes I might just say that the linear program is optimal, which is abuse of terminology, but makes life easier. Okay. And I asked you why this needs the proof. Does anybody have any thoughts on this? Why do we call this a theorem and not like an obvious fact? In particular, can you give me an optimization problem that is not a linear program where this theorem does not hold? So can you give me some optimization problem, a small example, where I'll give you a hint, it will be feasible, but it is neither unbounded nor does it have an optimal solution. Can anybody think of such? Yeah, go ahead.
Like the constraints, like instead of having less than equal to, you have strictly less than, like it won't be a
Exactly.
closed set.
Exactly. So for example, thanks. If you consider maximize x1 subject to x1 less than 5, right? This is not a linear program because we have this constraint, which is not a allowed constraint in linear programs, right? Notice that clearly it's feasible. X1 equal to 4 is a feasible solution, right? But at the same time, It neither is unbounded because 5 is a bound, but you also cannot find an optimal solution because you can get arbitrarily close to 5, but you can never really reach 5 because of the constraint, right? So this is an example which is feasible, but neither unbounded nor optimal. Okay, and that is exactly what needs to be proven. Like in 2 dimensions, you might think it's clear in 3 dimensions, but you can convince yourself intuitively. But how do you convince yourself in higher dimensions, right? And that is something we will be proving as a consequence of the simplex algorithm. So the way we will prove this is we will look at the simplex method in the next module. We will show that the simplex algorithm always terminates, and when it terminates, it will actually give you a certificate, which we will be discussing in the next module, that proves that either the LP is infeasible, or it is unbounded, or it has an optimal solution, right? Proof via simplex. Okay, but is the theorem statement clear, and is it clear why we need a proof? This is the part that needs a proof. Okay. All right. Okay, so that's about it. So one more thing I want to mention. Yeah, go ahead.
Sir, I have a question.
Yeah.
Sir, what does unbounded mean here in the second LP is unbounded?
Right. So unbounded means that here is, I think, the definition. I think I wrote it somewhere. Let's see. Right. So I did not really write it down as a definition. But for a maximization problem, this is what unbounded means. For any constant real number, k, you should be able to find a feasible solution whose value is strictly greater than k, right? This is unbounded LP for a maximization problem. And for minimization, you would want it to be strictly lesser than k. Does it answer your question?
Okay, so unbounded depends on the type of objective function.
It depends on whether it's maximization or minimization. Those are the only two possibilities we are, that's basically what is allowed in the definition of linear programming. Right, so it depends on the objective function and whether it is a maximization problem or a minimization problem.
In that case, in
Yeah.
the recent example which you gave,
Yeah.
in the last example, x1 is less than 5, right?
You mean LP3?
Yeah, today, the recent example, the example you gave today.
Right. Okay, this one. Right. Okay, got it. Here. Yeah.
So x1
Exactly.
is less than 5.
Right.
Okay,
Therefore,
as
it is not unbounded.
Okay, as the maximization problem, yeah, fine. Yeah, got it.
Right? Because for k equal to 5, I cannot find a feasible solution whose value is greater than 5.
Yeah, got it.
Right, exactly. So that's precisely the point I want to drive home, that this optimization problem, which is not a linear program, is neither unbounded nor optimal, using the same definitions that we used for linear programs, right? So when we defined it, I assumed that the problem is a linear program, but you can use the same definitions for any optimization problem. And now you see that this theorem does not hold for any optimization problem. Okay. All right, so we will prove this using the simplex method. There are other ways to prove it, which are not algorithmic, but we are not going to focus on them. In fact, I don't even know any of these proofs completely. I think I've seen bits and pieces. They are more algebraic, but we will focus more on the algorithmic side. So what we will do is we will see the simplex algorithm, which is not an efficient algorithm, but it terminates in finite number of steps. It may not be polynomial number of steps, but it will be a finite number of steps. We will prove that. And because it terminates, we will know that our linear program is either infeasible, unbounded, or it has optimal solution. And that will be our way of proving this theorem. Okay, so it will be an algorithmic proof in a sense. Okay. One point I want to mention is we are discussing linear programs in this course because one of the main goals of the course is to use the theory of linear programming to solve combinatorial optimization problems like the minimum cost perfect matching problem, the shortest path problem, etc. Right? However, linear programming in itself is part of optimization theory, also called operations research, where people study other types of optimization problems. And one generalization of linear programming is called convex programming or convex optimization. So we won't be discussing convex optimization in this course, but almost everything that you see in linear programming generalizes to convex programming. And one of the reasons linear programs are easily solvable, both in practice and in theory, is because of convexity. And it is for this reason that I do want to talk about convexity, but there are also other reasons that I will mention during this discussion. Okay, so I want to now switch to convexity. Okay, what we will see is that the feasible region of any linear program, we know it is a polyhedron. It could be a polytope. In particular, that set, the feasible region, is a convex set. But we need to define convexity before that. Okay. Are there any questions or concerns? All right. Okay, so let me also give you another motivation. We talked about corners yesterday, right? And they are formally called extreme points. So if you're given a 2D object, a 2D convex polytope, or a 3D one, you know what the corners are, right? Intuitively, you know that the corners of a cube, if I give you a 3-dimensional cube, there are going to be 8 corners. So what is a mathematically precise way of defining corners? Anybody? Does anybody have any idea how you would define corners? Or what is something special about corners of a cube that separates it from the rest of the points of a cube?
Those corners are unique points that a face can have multiple points, but a corner can only have one point.
Right, but so we are using the term face and corner, but can you give me a sort of a geometric kind of property that is satisfied by the corners, but it's not satisfied by any other points in the cube?
So it has
Like why do
three
you know?
different
Yeah, go ahead.
planes intersecting at itself.
Right, okay, that is one way of thinking about it, and that is also something we'll be proving. Okay, so it has 3 different planes intersecting at that point. These are planes that define the cube, right?
Yes, yes.
Right, right. Okay. Any other way of looking at it? So this is also a viewpoint that we will be proving soon. But is there any other way of looking at it? I'll give you a hint. Think of a line segment. Can you think of this in terms of a line segment joining 2 points? Okay, so while you think about it, I'm going to start a new page. All right. So let's draw a cube. Okay. So not a perfect cube, but I want you to think of it as being a perfect cube in 3 dimensions. So these 8 points that are the corners, what is so special about them? And I want you to think of drawing a line segment in 3-dimensional plane and then thinking about what is so special about these corners that's not true for the other points.
Through the corners, we can draw a line segment which doesn't go through the cube at all.
Right, exactly. And they are the only points where any line segment you draw that is not just the point itself, it is not a trivial line segment, which is just one point, right? Any line segment you draw through a corner, so basically for a corner, you can put a line segment like this, which meets your object, the cube, in exactly one point, which is the corner, right? However, for any other point, you will be able to draw line segments that are completely contained inside the cube itself.
Is it like there exists a line segment which will only pass to the point? Is that what you're telling?
So I want the point to be not an end of the line segment. So this is a line segment that contains the corner, the particular corner we are looking at, as a point, as an interior point. What I mean by interior, it's not one of the two ends. So if the line segment has two ends, A and B, the corner is some point C, which is not the same as A or B.
I mean, we can find these line segments even on the edges, right? We can choose a point on the edge.
Right. You can make a line segment like this, for example. Is that what you mean?
No, not like that. In the same way as AB, but on the edge.
Okay.
Then it'll be just a single point interior on AB.
Exactly. My point is that for a corner, if you draw any line segment which is completely contained in your cube, then the only line segment that will contain that, the only point in that line segment will be exactly your corner point. Let me try to make this a bit more precise. Let's see. Okay. So what I want to do is I want to draw a line segment that is completely contained in the cube and that contains my corner. But the line segment should not be just one point, right? It should be a more interesting line segment. It should have it will have infinitely many points, right? If it is not one point, then it has to be infinitely many points, right? So I want to draw a non-trivial line segment that is completely contained in my cube and also contains the corner. And that you cannot do for the corners. You can do for any other point in your convex object, but you can't do it for the corners. If you draw any line segment, it will be outside, it will have some points outside your convex object. Does that make sense?
I'm still confused. Like
Okay, let's not worry about it. So let me put down formal definitions and then we'll come back to this discussion. Okay, so let's not worry about all right, so let me just put down some formal definitions and then we will come back to this discussion, okay? And you'll see what I'm trying to convey. I think I have not found the best way to explain it.
Sir,
Okay. Yeah,
Sir.
go ahead.
Sir, I think the difference between corner and the edge is the points on the edge you can do two ways. Either you can create a segment like AB which touches the edge at a single point, or you can create a segment AB along the edge such that it completely
Right.
fits inside the edge. But
Exactly.
the second case is not possible for corners.
Exactly. The second case is not possible. Right. Yeah. Yeah. So that is precisely what I'm trying to convey. Let me put down some formal definitions and then state it in a more formal language once we have the terms for it. Okay. All right. So let's look at any 2 points in Rn. Okay. So I have two vectors, two n-dimensional vectors in this space. And actually, let me start with one small example. Everybody is comfortable with 2 dimensions. So let's start with that. Supposing I take a point 1, 1 and 4, 4. Actually, since I have these squares here, let me make use of them. Let's say I look at 1, 1 and 4, 4. Okay. This is the line segment joining the 2 points. These are my 2 points, x prime and x double prime. Okay. How would you define what is the midpoint of this line segment? Anyone? For this example, what is the midpoint? What are the coordinates of the midpoint?
2.5, 2.5.
2.5, 2.5. Right. Okay. Can you write 2.5, 2.5 in terms of 1, 1 and 4, 4? I'm not trying to make it very precise, but hopefully you get the point.
Yeah, half of
Half
x
of,
dash
exactly.
plus half of x dash.
Exactly. It is exactly half times x prime plus half times x double prime. Okay. How about this point, 2, 2? It is like if you're thinking of the line segment from 1, 1 to 4, 4, it is like the point 1 at the 1/3 position, right?
Yeah, I mean any point on this line you can write it as alpha times x dash plus 1 minus alpha x double.
Exactly, exactly. And this point is exactly 2/3 times x prime plus 1/3 times x double prime. Do you agree? And that is actually how you define a line segment. It's lambda times the first point plus 1 minus lambda times the second point, where lambda is anything between 0 and 1, right? So if you look at the set x bar, which is lambda times x prime plus 1 minus lambda times x double prime, for all values of lambda between 0 and 1, that is exactly the line segment with ends x prime and x double prime. Okay. And notice that when lambda is equal to 1, you are exactly at the first point. And when lambda is equal to 0, you are exactly at the last point. Right? And as you keep going from 1 to 0, you're basically moving along this line segment from x prime to x double prime. So this is your line segment with ends x prime and x double prime. Okay. And this way of writing x bar is called a convex combination. So x bar is a convex combination of x1 and x2. Sorry, x prime and x double prime. Okay. And if you take all the possible convex combinations, you get exactly the line segment joining these 2 points. Okay. Good. Right. So now we can actually make things a bit more precise using these terms. So look at this corner. This corner cannot be written as a convex combination of two distinct points that are in your cube. So if this cube is the set S, okay, so this is my S in 3 dimensions, right? For the corners of the cube, you can never write them as a proper convex combination of two distinct points. By proper, I mean lambda cannot be 0 or 1. Okay, so a convex combination is proper if lambda is not 0 or 1, right? Because that just gives you the two ends. Right? So for the corners, you can never write them as a convex combination of 2 points in the cube. But for any other point in the cube, you can always draw a small line segment around it and write this point as half times this point plus half times the other point. But you cannot do this for the cube because the moment you draw a line segment with this property, that line segment will leave the cube. Does that make sense? That is what I was trying to convey, but yeah, I did not have the words for it, so it was becoming too complex.
Yeah, it's clear now.
Does
And
everybody see this?
And in R3,
Okay.
it should be just lambda I not equal to 1, right? That's the condition.
It should be what? Lambda.
For the proper convex combination.
Right.
You wrote lambda not equal to 0 or 1 below. So it should be.
Yeah, so basically what I don't want to write a corner C as 1 times C plus 0 times C, right? That is always possible.
Yeah, I mean, if you take
Or,
a point on the edge, like one of the lambdas can be 0. So
right, exactly. So that would suffice, but this also works, right? Because I could keep one of them as, so basically I want two distinct points. If you just say that the 2 points are distinct, it automatically implies it has to be a proper convex combination.
oh, okay, right. It's
Right.
2 points only, correct.
So, right. So the observation I want to make, and we will be proving these things rigorously. The corners of a cube are the only points that cannot be expressed as a proper convex combination of two distinct points. In the cube, right? So I want these 2 points to also be in the cube. Okay. For any other point of the cube, you can draw a line segment around it, which is completely contained in the cube. And therefore that point is a convex combination of the two ends of that line segment. Does that make sense? Are there any questions or concerns regarding this discussion? Okay. So I hope that makes things a bit more precise with these terms that we have. Okay. All right. So we want to prove this rigorously. That is one of our goals. We will prove a more general observation for polyhedra. In fact, I shouldn't say, this is actually going to be our definition of extreme points. So this is the way we are going to define extreme points. It's not something we are going to prove actually. It's just the mathematical way of thinking about corners. Okay. So that will happen. But before that, let's talk about what a convex set is. Okay. So a convex set, okay, so let's just look at 2 examples in R2. Okay, they're a bit too close. Let me make some space. Which of these is convex? For those of you who have already seen convexity, or if you already...
First one.
First one is convex, and the second one is not convex, right? And can we think about this in terms of a line segment? Why is the second one not convex? Can you give me an explanation in terms of a line segment?
Line segment from the top half to the bottom half contains points not in the field.
Exactly. So you take 2 points, x prime and x double prime, and if you consider the line segment joining these 2 points, it leaves the set. It is not completely contained in the set. And this is exactly what it means for an object to not be convex, right? Whereas in a circle, if you take any 2 points, the line segment joining them will be completely contained in the circle. That is also true for 2 points which are on the boundary, right? So that's going to be exactly the definition for convexity. So a set S in Rn is convex if the following holds. For any 2 points x prime and x double prime in Rn, the line segment with ends x prime and x double prime is completely contained. I mean, I don't need to say completely contained. I can just say it is a subset of the same set, right? So that means if you look at the set x bar, which is all the points that can be expressed as a convex combination of the 2 points, right?
So should that be x dash comma x double dash belongs to S, sir?
Oh, yes. Thank you. For any 2 points in the set, we want the line segment to be contained in the set as well. Thanks. Right. So we want this set to be a subset of S. Okay. Or in other words, any convex combination of the 2 points belongs to the set S, right? This is the same as saying any convex combination of x prime and x double prime belongs to the same set, right? So we have at least 2 or 3 ways of thinking about it or writing it. Okay. And then, yeah, go ahead.
Is this Jensen's inequality? This,
No, there is no inequality here. We are just writing down the definition.
okay, because I saw something very similar to this one.
Right. So typically you use the term inequality, Jensen's inequality. I'm not sure what exactly it is. I think I've heard of it before. Typically it refers to a result that needs to be proved, right? But here we are just using this. This is just the definition of our convex sets. So we are not proving anything. This is just the way a convex set is defined. Right? Okay. Good. All right. Any questions or concerns? Right. So we know what a convex set is. Right. And we use the concepts of these convex combinations and the line segment in order to define a convex set. Right. Okay. Great. All right. So what are the kind of things we want to prove now? Well, as I said, the reason we are looking at convexity is because it's an important property as to why linear programming has such a nice theory, which does not apply to arbitrary nonlinear programs and other kinds of optimization problems, right? But the theory of linear programming, almost all of it, does generalize to convex programming. So instead of linear functions, you could have convex functions, and I'm not an expert on convex optimization. In fact, I barely know much about it. But what is true is that convexity is an important property of linear programs that makes all of this theory work very nicely, right? And that is the reason I want to talk about it. Also, it gives you a geometric intuition, which is related to our previous discussion in this module. Okay, so one of the things I want to prove is that the feasible region of any linear program is a convex set. So one of our main goals in the rest of this module is to prove that the feasible region of any LP is a convex set. Okay, and recall that the feasible region of a linear program is exactly the same as polyhedra, right? Which is the intersection of a finite number of half spaces. Okay, every polyhedra can be written as a feasible region of some linear program, because for the polyhedra you just find out all the hyperplanes that define that polyhedra, and those will be your constraints of the linear program. You don't really need an objective function. You can put any objective function you like, right? We are talking about the feasible region, so the objective function doesn't really matter, right? And we have already seen that the feasible region of any linear program is in fact the intersection of finite number of half spaces. Therefore, a polyhedra by definition. Therefore, a polyhedron by definition. In fact, I should use singular here. Okay, so that means that it suffices to prove that polyhedra are convex sets. Okay. Are there any questions or concerns at this point before we proceed to prove this result? Let us go back quickly to our example that we discussed in the last couple of lectures, right? If you look at this example, for example, linear program 2, you can see that this polyhedron in 2 dimensions is a convex set. If you take any 2 points in this region and you draw the line segment joining those 2 points, that line segment will be completely contained in this region, right? Okay, so that is exactly what we are about to prove now. Okay. So how do we prove this? Anybody has any thoughts? I would like to know your thoughts on how we would prove such a result. I want you to focus on the definition of a polyhedron. So let's look at this definition. A polyhedron is the intersection of a finite number of half spaces. So what should we prove in order to get
If
to our
x1 and x2 satisfy a constraint, then the convex combination also satisfies the constraint.
Great. Exactly. In other words, you're saying that half spaces are convex. Is that right?
Yes, sir.
Right. Okay. You are actually what you said is that we prove first. So here are the steps. Let's see if this works, right? So one possibility is to first prove that half spaces are convex, which makes sense, right? If you draw any half space, it seems to be convex, right? Any point in that half space, any 2 points in that half space, if you draw the line segment, that will be completely contained in the same half space. So we could prove that half spaces are convex. And then what else would we need to prove? This is our first step. We'll prove that half spaces are convex. Now, how do we complete our proof?
So similar to that line segment lambda 1 minus lambda, we'll do like spaces too.
So are you saying how we would prove statement 1, or are you saying what the next step would be?
Next step for the line
Okay.
segment, we used lambda 1 minus lambda linear combination to get
Yeah.
a point in between. So like we'll do similar for half spaces too.
Right. So I'm not able to. So that would be useful in the first step itself. But once we have proved that half spaces are convex, after that, how do we prove that the whole polyhedron is convex? I think what you are saying is more relevant to the first point itself, but what I'm looking for is the second step. How do we go from half spaces are convex to all polyhedra are convex? Go ahead.
Showing intersection of half space are convex. So maybe
Right. Okay. We want to get to the intersection, but we already know that the half spaces are convex. So can we prove something more general, something more abstract?
intersection of convex set is convex.
Exactly. Let's prove that the intersection of any two convex sets, or in fact any number of convex sets, is a convex set. Right? That is exactly what we will prove. We will prove that the intersection of any number of convex sets is another convex set. In fact, we don't even need this to be finite, could be infinite, doesn't matter. Okay. So let's make sure that if we prove these two things, then we are done, right? We are going to first prove that half spaces are convex. That's not going to be very difficult, as you will see. And then we are going to prove something even easier actually, which is that the intersection of any number of convex sets is another convex set, right? And if we prove these things, then we are done. That implies that the feasible region of any linear program, or in other words, any polyhedron, is a convex set. Okay, are there any questions or concerns? So let's see, we have another 3 minutes left as per the official timing. So let's see which one we should do. Let's look at number 2. That's actually nicer in some sense. It's very intuitive. So let's try to prove the second statement first. Okay. Let's try to show that the intersection of any number of convex sets is another convex set. Let's just take two convex sets, S1 and S2. Let's say these are two convex sets. If you like, you can think of them as being in Rn, doesn't really matter. And what I'm drawing now is a Venn diagram. Okay, so this is not a polyhedron polytope kind of diagram. Let me write it down explicitly so that there is no confusion. This is a Venn diagram with the sets S1 and S2. Okay. So what we want to prove, we know that S1 and S2 are convex sets, and we want to prove that their intersection is a convex set. What does that mean? What does this mean? If I take any 2 points x prime and x double prime in the intersection of S1 and S2, what do I need to show?
Any point on the line segment joining those two is also in the intersection.
Exactly. For all x prime and x double prime, we want to show that. In fact, let me just put it slightly differently. let's say L is the line segment joining x prime and x double prime. Okay, and what we want to show is that L is also contained in S1 intersection S2. Okay, I'm not going to write down any lambdas and 1 minus lambdas because they are not necessary for this proof. I want you to think of it as a slightly more abstract level. Okay, so for any 2 points in the intersection, so x prime is here and x double prime is here, and we are considering the line segment joining them. I'm not going to draw a line segment here because this is a Venn diagram. Okay, we want to prove that this line segment is completely contained in S1 intersection S2. Can anyone complete the argument?
That line segments points are also, I mean, S1 and S2, right?
Why? What are you using here?
I mean, the line segment points belong to S1. They also belong to S2. So they
To S2.
Exactly. Exactly.
Right.
Exactly. So these 2 points, because they are in the intersection, they both belong to S1 and they both belong to S2, right? Because they both belong to S1 and S1 is a convex set, the entire line segment joining them is contained in S1. Similarly, the entire line segment joining them is contained in S2, and therefore the entire line segment joining them is contained in the intersection of S1 and S2. Right? So the main point is, since x prime is in S1, x prime and x double prime, both of them, and S1 is convex, we know that the line segment is completely contained in S1. Likewise, the line segment is completely contained in S2. Well, if it is completely contained in S1 and S2, then it basically means that it is contained in the intersection, right? So that's your argument. And this is the proof for 2 sets. But if we prove it for 2 sets, we are done, right? If the intersection of 2 convex sets is convex, then you can just do repeated intersection, or you can do the same argument for all the sets at the same time, whichever you prefer, right? So there are at least 2 ways to complete. Either you do repeated intersection, or you just take all the sets at one time and complete your proof the same way. Right? So do it yourself. Generalize to any number of sets. So we did it for 2 sets, and I would like you to write down the proof for yourself for any number of sets. Okay, and let me give this a name, 2.17. So they call it a remark. I don't like remarks. I'm going to call it a proposition. The intersection of any number of convex sets is another convex set. Okay, and I'm just going to say hence proved because we proved it for 2 sets, and you can generalize the proof to any number of sets. Okay, and what I want you to try on your own before tomorrow's lecture is the following. I want you to try proving 2.16 on your own, that half spaces are convex. Right? And I'll just give you a brief idea of how to start. Let's consider any half space H, X such that A transpose X less than equal to beta, right? Any half space is a set of solutions to a linear inequality, right? and you want to show that this is convex. So that means that for any 2 points in H, you need to show that any convex combination belongs to H. Okay, and I would like you to try it yourself doing this last part. Okay, we'll complete it tomorrow. It's not difficult. It's just a matter of writing down a convex combination and expanding the expression and checking why it goes through. Okay. All right. So that's all for today. And once we prove this tomorrow, we will have proved that all polyhedra are convex sets. And in particular, the feasible region of any linear program is a convex set. Okay. And then we'll discuss a little bit more about convexity. We might even finish the discussion on convexity tomorrow or on Monday, and then move on to module 3. Yeah. Okay. I'm here for another 5-10 minutes if there are any questions or concerns. So maybe I'll stop recording if there are no questions, but I'm still going to be here.